time we were discussing determinants, right? So if NLJ is an n by n matrix in some field K, then we define its determinant via permutations like this, right? It's summated over all permutations. We have sign of sigma and then a 1 sigma 1 a and sigma, right? This is this summation. Using this, we can actually derive many formulas for the determinant and so on. But instead, we will give an alternative definition. Şey yapıyor, bir matris ve biliyorlar linear transformation gibi yazdık. Okay, so all right, so if we are given a matrix like this, we can define linear map, right? From V to V. We can take these to be, for example, K and 1, n by 1 matrices, column matrices, and so the linear maps now defined by with the matrix representation. Data equals. So what we mean is the following. Let B be the standard basis, meaning that EI is just 1, 0, 0, R here. So the R place. Okay. And A is the matrix representation of what? Think of EI is just summation A neydi? J I değil mi? Yok. J kalın olacak. J kalın olacaksa EI J kalın. Evet. Dolayısıyla J'den şey yapıyor. Tamam. Evet. EI'nin görüntüsü ait kalın. Dolayısıyla A1I, A2I, A3I, and so on. So this is the ith column. And then we look at the following. So P of E1, which is E1. So what is the value of these gadgets? You see, what is TE1? TE1 is this. A 1 1 E1, A 2 1 E2, up to A N1 En wedge product TE2. What is TE2? A1 to E1, A2 to E2, up to A and to E2, right? This is the second column. This is the first column of the matrix A. This is the second column. And we just multiply up to A1 and N1, A2 and A2, up to A and B1. Right? And we have to multiply these gadgets. Well, we know that how many terms we will have. Here I have n choices. Here I have n choices. But we know that if I choose, for example, the E1 term, then I shouldn't choose E1 here because E1 is 0. So I have to choose n-1 terms. One of the n-1 remaining terms. For the third row, if I choose E1 here and E2 here, I have to pick up a basis element which is not E1 or E2. So I have n-2 choices. So it will go like this, and I will have at the end only one choice because n-1 of them are picked. So there's only one left. So in total, I have this many terms. What is this? It is just n factorial, right? And if you open this up, what you will get actually, so T1 which T-N will be just the following. So summation over, let's say I choose, okay, sigma 1, so E sigma 1, okay, E sigma 1, and then in the second one, E sigma 2, E sigma n, right? Here, sigma is what? Sigma is a permutation, so sigma is an element, from this set, a one-to-one function. A one-to-one function. So from this one, let's say I choose 2, from this one I choose 1, and then I choose 5, and so on. Right? A one-to-one function. Summation of essence. And if you choose, of course, sigma 1 here, if this is sigma 1, then the coefficient is just 2, 1. So the first coefficient is just sigma 1, 1. The second coefficient is sigma 2, 2. You will go up to nth term, so sigma n, and then here I have E sigma 1, H E sigma 2, H E sigma n. But I know that, right, this is just a permutation of the basis elements. I can reorder them by interchanging this element and write this as E1 wedge, E2 wedge, En. But to obtain this one from this one, you have to make permutation, transpositions. And those, each transformation, each transposition changes the sign by -1. And you know that the number of necessary transformations is just some number, and then you just raise that you put that number about -1. So we have this. And this thing is also has a name. It is called signature of sigma or sign of sigma, sign of permutation sigma. It is +1 if it's an even permutation. It is -1 if it's an odd permutation. And that means what? Every permutation can be written as a product of transpositions, and you just count the number and see if it is even or odd. If it is even, then it's an even permutation. If it's odd, it is an odd permutation. So what we see is that this summation is just what? So here I have sign of sigma, and then A sigma 1, 1, A sigma 2, 2, A sigma n, and then E1 H E1. Okay. Well, you see, this E1 H E1 term is always the same. So what we get, just this number, I'm sorry, this number times this gadget. So this TE1, which TEN is just some number. Let's say, let me just say lambda times E1 HEN, and this number is just this gadget. Sign of sigma A sigma 1, 1, sigma 2, 2, up to sigma and n. It is almost this gadget, right? It's almost this gadget, but not quite, right? Here I have 1 sigma 1, 2 sigma 2, but that sigma 1, 1, and so on. It's kind of a transpose of that thing, right? But we make the following trick. Şöyle diyeyim. Yes, so if sigma I equals J, then sig and tau is the inverse of sigma, then tau J is equal to I. Where tau is the inverse transposition, so this is the identity, right? Any permutation has an inverse, and this to satisfy this schedule. So if permutation sigma sends I to J, then tau sends J to I. So what I will do, I'll just replace this gadget with tau. How? Well, sigma 1, 1, sigma 1, yani bunu yerine şunu yazabilirim. This is just 1 tau 1, right? Yani tam o değil de.
Hocam yanlış olmaz. Çünkü mesela A'yı matris gibi düşüneceğiz ya, hani A matris ya.
Evet.
Biz yukarıda sigma ile beraber o bir sabit
Yani şöyle. Evet. Okay. Aynı şey olmak zorunda da işte onu göstermeye çalışıyorum. Okay. What I'm going to do is the following. Sigma 1 is equal to some number, right? It's some K. Therefore, here I have so A sigma 1 is just A K 1, but 1 is just tau K, right? Because they are inverse each other. So this is just A, K, tau K. So instead of A sigma 1, 1, I can write A, K, tau K for some K. For this one, I will write another term, right? A, let's say L, sigma L. And I will go how many terms? N terms. So let's say Z, tau Z. Evet. Right? First one, second one, and the nth one. But, you know, one of them is one, right? One of these cases is one of them is two, and so on. So this is nothing but actually one of these integers is one. So I have actually 1, tau 1, and then one of them is 2. So I should have 2, tau 2, and one of them should be 3, and one of them should be n. So I should have this. Değil mi? Ya bunlardan bir tanesi 1'e tau 1, bir tanesi 2'ye tau 2. Hangisi bilmiyorum. Ama bir tanesi öyle, bir tanesi öyle. Sonuçta bu çarpımla bu çarpım aynı şey. So what we see is that I have sign of sigma and I have this. With this, but then look at the following. So T1 which T is just okay. Summation sign of sigma, and then here I have 1 tau 1 and tau n. Here, of course, tau is the inverse of sigma. So for each sigma, I am using its inverse. But then, of course, I can just write this summation over just tau. Right? So I have 1 tau 1 and tau n. What about this sign? Well, whatever sigma, if sigma is, let's say, product of K transposition, say, let's say A1, B1, A2, B2, AK, BK. What is sigma inverse? Nedir bunun tersi? Bunu ters sırada yazacağım, değil mi? Yani AK, BK, A2, B2, A1, B1. Right? Inverse is this. If this has K elements, then this has K elements. Therefore, this sign is the same as sign of tau. So what we see is that this product, not that product, this is lambda, actually. Right? This is lambda. Here. So this product is lambda times this, and I am computing lambda. Lambda is equal to this thing. But this has already a name. What is this? This is just determinant of. Okay, determinant of. So what we have seen then, this indeed proves the following fact. Nedir o? Şu. Teorem olarak yazayım. So let P be and dimensional vector space over the field K and T an operator on V. So it's an operator on V, okay? It's from V to V, not anywhere else. Let beta E1, En be any basis. Any basis for T. Okay. Find it?
B.
V, yes. V. Then okay, then we have what? TE1, which TEN is just lambda times this. And lambda is just determinant of A times E1, which En, where A is the matrix representation of T from data to the. Okay. But note that evet. Şimdi şunu söyleyebilirsiniz. Determinantı tarif ettik. Yani bu T'nin determinantı değil de, right? This is not the determinant of T, but determinant of the matrix representation. What if I change the basis? So the question is this. We proved this, but the question is this. If we replace beta with beta prime, do we get this? So determinant of A, determinant of A prime. A prime being the matrix representation of A, T in this space. Yani matris gösterimi değişirse bu da değişir. Tamam mı? Onun değişmeyeceğini de şöyle söyleyebiliriz.
Hocam, can I ask you?
Yeah.
Hocam, da aynı base'ler.
Evet, aynı liste.
We just recently proved that A sigma 1 is multiplication equal to A1 power 1.
Yeah.
Why we didn't define the beginning determinant as like that? I mean, we defined determinant as a sigma 1, but it will define it as A1 power 1.
Well, I mean, they are equivalent definitions, and each one has its own actually advantages. And we just see that they are the same objects. But sometimes seeing determinant like this is advantages, and sometimes seeing determinant as the determinant of matrices advantages.
And will we define determinant for n times n matrices?
No, it doesn't exist.
Doesn't exist.
Yeah. Only for square ones. Okay, now, so question is, if we replace the basis with another basis, so we get another matrix representation, are they the same? The answer is yes. So, yes. So determinant of A is the same as the determinant of A prime, where A is the matrix representation of P in the basis beta, and A prime is the matrix representation in beta prime. Okay, and that's why, hence, this common number is defined to be the determinant of, yani bu bazdan bağımsız olduğu için sadece T'de belirleniyor, right? So this number is independent of the basis. It is determined only by T, the operating T. Therefore, I can just call it the determinant of T. And why this is the case? So why okay, we can see it as follows. Evet. Ama şimdi T'nin burada şunu gördük, yani başka bir basis alsam burada, hani şuraya prime koysam, prime koysam, bu sayı aynı kalacak mı? Efendim? Kalacak da işte onu göstermemiz lazım. Onu söyleyeyim. Bazdan bağımsız. Nasıl kalır? Şöyle. Okay. So claim is this: if beta P1 Pn and beta prime P1 prime Pn prime, then şimdi bakın bu sayı nedir? Bu sayı şunu sağlıyor. Bu çarpım bunun bir katı. Kaç katı olduğunu söylüyor, değil mi? O zaman şunu yapmam yeterli olacak. If this is the case, then P1 Pn is equal to lambda E1 in n, and P1 prime Pn prime is equal to lambda E1 prime Pn prime for the same lambda. Yani şeyi değiştirmem, basis değiştirmek, lambdayı değiştirmek anlamına gelir. Lambda değişir. Peki bunu nasıl yaparız?
Şuradaki data tanımı.
Efendim?
Şuradaki data.
Hangi data? Lambda mı?
Ya onların birbirine eşit olduğu için pardon. Yani onların birbirine.
Şöyle ama işte bir baz için A varsa öbür için A prime var. Yani matris değişebilir ama determinantı değişmiyor. Değil mi? This matrix is doesn't have to be same. For a basis, I have this matrix representation. If you change the basis, you get another matrix representation. So matrix can be changed. It depends on the basis, but determinant, this lambda doesn't change. Okay, if I choose another basis, I still get the same lambda.
Then we will show their And if you divide them all, then we will get all the same division, right? If we TEIs divide to EIs, range product, then all the results will be the same.
Nasıl?
Yani TE1'den TE'ne kadar range product'ları E1'den E'ne kadar bölsek hepsinde aynı rakam.
Evet. Ya bu da şunu da gösteriyor aslında, değil mi? This means what? I have some basis vectors. Their wedge gives me volume of some parallel pipette in end space. What does this means? You map each vector via this operator. So these vectors are sent to some vectors in the same vector space. You compute the volume of that parallel pipette. It is lambda times the original parallel pipette. If you choose basis, this doesn't change. And this is actually what it should be, because this operator T changes volumes by multiplying with a number, right? For example, T multiplies volume by 5. But it doesn't matter which parallel pipette you choose, right? Any parallel pipette will be just mapped to another parallel pipette with whose volume is just 5 times the original one. Değil mi? Yani bu onu söylüyor. Hangi paralel pipet alırsanız alın, onun hacmi lambda kadar arttırılıyor. Başka bir paralel pipet alırsanız onun da hacmi aynı sayıda arttırılacak. Aynı katsayıyla çarpılacak. Onu söylüyor. Ki öyle olması lazım. Hani bir tane paralel pipet alıyorum, onun volümünü 3 katını arttırıyor. Başka bir tane alıyorum, onun 2 katını arttırıyor. O olmaması lazım. Tamam mı? O yüzden hani bu şey olacak bir şey değil. Peki nasıl ispat ederiz?
We will write EI's prime in terms of E1 and look at that range problem.
Böyle yapabiliriz. Bir dakika. İnce bir yolu bulmaya çalışıyorum. Yok öyle değil de bazı değiştirme olayını düşünmemiz lazım. Bazı değiştirmeyi düşününce tabii şeyi yapmadık. Biz nasıl yapabiliriz onu? So the matrix representation, matrix representation of P in the basis beta prime is just the matrix representation of P from beta to beta, and then here I have identity operator from beta to beta prime to beta, and then identity from beta to beta prime. So if this is let's say bunların milleti diyoruz. So this is let's say A prime, this is P and hangisine verilmiş? Fark etmemiş. Birine verilmiş. Yine elinizde böyle bir şey var. This is the representation of T of the same operator. Here. Yes.
Hocam sağdakileri veriyormuş.
Efendim?
Sağdakileri veriyormuş.
Şöyle mi? Buradan yaratabileceğim mi? Yine bir şey yapsak, ayları şeylercesinden yazınca işte P maddesi gelecek. Şimdi ayları şeylercesinde yazınca
Hocam tek şeyleri yapamaz mı? P ile P(x)'nin çarpımlarının determinantı 1 olacak zaten. Aslında çünkü. O zaman P(x)'nin determinantı P'nin determinantının 1 bölücüsü olacak. Çarpımda birbirine.
yani işte ama determinant olunca bunların yer değiştirdiğini söyleyebilmek lazım.
Yani yazmışız. Ona bakma da determinant A çarpı B işte determinant A çarpı determinant.
Onu nereden yazmışız?
Yazmışız ama.
O doğru da hani ispat etmek lazım. Okay, let me break, let me think about it, okay, and then we'll continue.